come on, about trying to go through this reaction again. Okay, bromine and chlorine reacting with double bonds. Okay, they're in a very particular or special kind of arrangement here, and I'm going to attempt to show it with the model kit. So maybe I shouldn't be recording because no one's going to see it. If we had a standard alkene, so this is supposed to represent an alkene. The white and the green are the orbitals, okay, the p orbital. So each lobe of the p orbital in this model kit. Okay? So when we're going to look at a bromine reaction, add some pieces together. We'll go ahead and call this red atom our bromine. It's going to use the larger model kit, except I can't find it. Okay? So bromine is fairly large, and because of that, is easily polarizable. So what it can do is kind of sandwich itself in between the p orbitals. Okay? And so what those p orbitals end up doing is saying, hey, we can form a bond with that bromine. So they no longer are p orbitals because we're forming that bond, and we get an exchange into sigma bonds. So what we end up transitioning, I don't have enough hands to do this. Okay? The bromine comes in, our double bond reacts. I have arrows, I don't have arrows. Our double bond reacts and shuttles electrons out towards the bromine. Okay. And so we break those bonds. So the double bond electrons come out, react with the bromine. The bromine then breaks off the other bromine. It takes the electrons, say that worked, took the electrons of the bond. So we get bromide. And then our bromine kind of sits in between and forms a bond between those two groups, okay, between our two carbons. Okay. And the process of doing that, okay, we end up changing the hybridization of the carbon atoms. They go from being sp2 to sp3, which is why we see, if you look at it from the side, our carbon groups that we're all in the same plane and are, which is the reactant side for you guys? This side? This side. All right. Those carbon atoms that were all in the same plane originally now pucker out of the plane. Okay? So you can see that kind of bond angle, and that's because that central carbon, where I'm attempting to point with my pinky, is now sp3 hybridized. We changed the hybridization of it. Okay? One of the other repercussions of this, now that we've got this structure, is that this bromine cannot form the double bond or the ring this direction. Okay? I mean, even as I try and physically make a trans ring, it wants to rotate and force the bond to occur on the same side of our ring. So if we looked at our double bond again, our bromine comes in from the exact same side. So our ring is on the same side of the double bond. Okay? That's what's attempting to be shown here. So what we've done here with our central structure is we're assuming everything's flat, and we draw out cycloalkanes. We typically draw them flat anyway, and we try and show our substituents as either wedges and dashes. So in this case, where did it go? In this case, what we're trying to say is that that bromine is now coming out of the plane at us, where these carbons are all in the same plane. Okay, kind of see it? That gives us this intermediate. If we kind of turn it on end and rotate that pointy carbon in front up out at you, we can kind of see it from the end where our bromine is aimed up. That's where we're looking at something like that. Go ahead and make these hydrogens so it looks a little bit easier. Okay. Everybody see that? Okay. So now the question is that structure stable? Well, is a cyclopropane a particularly nice structure? Okay, what's the bond angle in there? And an equilateral triangle. 60 degrees. It's supposed to be what? It needs to be 109.5 because what's the hybridization of that carbon? sp3. So that ring structure is highly stressed, okay, just because of the ring strength or the angle strength. Taking a step further, what charge is the bromine in this structure? Positive. Does bromine want to be positive? No. So that makes these carbons back here extremely reactive or extremely electrophilic. They want some electron source to stabilize it. Okay? So at this point, we can now shift out into solution and see, is there a nucleophile? Do I have something that has a source of electrons that can react and stabilize those carbons? And at the same time, hopefully destroy that ring. In this case, we've got the bromide ion floating around. That bromide ion can come in and react. Okay? When it comes in and reacts, though, if it comes in from the top, we would get a product where our bromines are both wedges coming up out, right? Except what does this bromine have a lot of? Electrons. And the bonds? Also electrons. So this bromide, when it comes in from the top, sees electrons, and our bromide has a lot of electrons. So what happens when it comes in from the top? Repels away. We don't get a reaction. The bromide must come in from the bottom. When it comes in from the bottom, there's nothing exposed there. So what ends up happening is we break, let's break that bond. We come in from the bottom and we break the bromine bond from our ring. That pops up. Because this is backside attack, we get an inversion of stereochemistry about that. So I can turn that around and I would form my bond down here. What's the relationship between those two bromines? Are they on the same side or opposite sides of the carbon-carbon bond? Opposite sides, so we would call them a trans product. Okay? So when we look at the reactivity of bromine or chlorine with an alkene or double bonds, we always end up with a trans product. Okay? The groups that we've added must be anted on opposite sides of the double bond. Okay?
So always, when it breaks, it always, the other part rotates around the same bond?
Yes. Close enough. Okay? And we end up with the trans product. The other term here that I said and kind of left off was the anti-addition. Okay? Hope this was on the next slide. Anybody see the pen? It's on the next slide. There it is. That syn versus anti-addition statement, okay, is ultimately referring to the same thing that we would get from cis or trans. It's just a different conjugation of the word. Sorry, don't look for it. It's not there. I just made it. Two groups can be cis and trans relations to each other. And in that case, we're kind of referring to it as a noun or an adjective. Okay? When we're looking at the syn or anti-additions, we're kind of looking at it as a verb, or it's probably an adverb. I'm not great with English, but it's just a different connotation, different application. So if I'm looking at a syn addition, I'm referring to the physical addition of two groups to the double bond. Okay? Depending on what's added, I might be able to refer to it as a cis or trans product. But say if I add two hydrogens, if I add two hydrogens as I do when I react an alkene with hydrogen, I don't really see cis or trans, okay? Because the hydrogens get added, and now applying cis and trans to that doesn't really make sense. Because when we're using cis and trans, we refer to cis and trans for groups that are not hydrogen. So to describe the chemistry of the reduction of adding hydrogen to an alkene, we would typically refer to this by the adverb terminology, and instead of calling this an anti-addition where they're on opposite sides, we refer to it as a syn addition. What we're saying is that the hydrogens are added to the same side of the double bond. Okay, we don't get any rotations about that sigma bond. That does not occur. Okay? So that's all that syn and anti-additions are referring to. Okay? It's if we can't really see a cis or trans product. So it's just a different application, ultimately the same idea. Does that make sense between cis, trans, syn, and anti? Is that a yes or a no?
Say it one more time.
Syn equals cis. Anti equals trans. If you keep that pairing, you should be fine. Okay. Syn and anti describe the reaction. Cis and trans describe a physical relationship. Okay? I wish I knew English better and I'd come up with a better explanation or comparison, but that's why I'm a chemist. Okay? Kind of makes sense, at least as far as syn and anti go. We good enough with that? You're not good enough with that. Okay. Are you comfortable with cis and trans? Cis equals syn, period. Trans equals anti. That's all you need. With all addition reactions. So cis and trans apply to everything. Syn and anti only apply to the addition reaction when you're reacting the double bond. Okay? Oh, it doesn't like me anymore. Get you back? Nope. Okay. So when we add bromine, we end up with our bromines trans to each other in a anti-addition reaction. Okay, so again, they refer to the same thing. It's just a question of how do you apply your definitions. Okay? When we look at the hydrogen addition, hydrogen is a much smaller molecule. So if we try to react with our propanes, this really isn't going to work because we don't have a scale set up here. But with our model, hydrogen's not big enough to interact with both p orbitals at the same time. Okay? It can't stabilize all that electron density, and so it ultimately doesn't make that cyclopropane-like ring that we get in the bromination. Okay? So because of that, we can't just react hydrogen with an alkene. Okay? We have to add something else to facilitate that electron transfer in the reaction. That's the role of the catalyst. Okay? All it's trying to do is help the hydrogen add to the double bond. That's it. Okay? And in the process of doing it, it adds to the same side. You'll notice that you don't really see any mechanistic arrows here. Okay, why not? No, it's not a bad guess, but no. Even if a reaction happens at the same time, we can show all those arrows. No. Are the electrons being transferred from the hydrogen to the metal, or are they being transferred from the hydrogen to the alkene? Is the alkene reacting with just the hydrogen, or does it react with the metal first? When it reacts with the metal first, does it actually form a bond to the metal, or does it just kind of sit on top? Okay? There's too many variables with how that reaction actually functions, so trying to nail down a specific mechanism, and in particular trying to teach it, is going to be virtually impossible. Okay? So it's one of the reasons why we don't teach the mechanism with this one. What you're responsible for knowing is that the hydrogens must add to the same side of the double bond. Okay? In what kind of an addition reaction? A syn addition. The hydrogens add to the same side of the double bond. Okay? So that will lock any kind of stereochemistry that we might pick up in the overall structure. Okay? Okay. So we can cover a little bit more on redox reactions. Oh, man, I just can't hold on to stuff today. We just talked about the hydrogen. So here's an example reaction where we're going to take a cycloalkene, methyl cycloalkene, We're going to react it with hydrogen, and we're going to have some catalyst. Okay? The alkene or the the hydrogenation reactions or our reduction reactions are kind of nice because we use really expensive metals. Okay? So if you ever get to do those reactions, you can steal all the chemicals. Okay? You're dealing with palladium or platinum. Sometimes you'll see nickel as well. Why would we use nickel? It's cheaper. That's about it. Okay? But it does the exact same thing. When we go through to look at our product, you'll notice that I've added the hydrogens. I didn't do a very good job showing these. But our new hydrogens, let's say they were added, let's make them red, were added on the same side of that double bond. So that would be these hydrogens. Where did that dashed hydrogen come from? I think I heard it. It was already there. Okay, it was implied. Okay, so you've got to remember that those hydrogens are still present. The hydrogen and the methyl that were on there to begin with got forced away from the reacting hydrogens, okay, or from the metal surface, and got pushed, in this case, back. So our hydrogen molecule that reacted came in from the outside, up directly against the screen, pushing the methyl and the other hydrogen away. Okay? Yes?
When you say same side of double bond, would it be possible to have them go on the right?
Yes. How would we get that? Where would the hydrogen molecule have added then? How can I get my methyl, this methyl, and this hydrogen in the product to be wedges? Kind of. Where's the hydrogen come from? Instead of coming from the front, pushing the methyl and hydrogen away, it's going to have to come from the back side of our plane. When the hydrogen comes in from the back side, that's going to force the methyl and hydrogen forward coming at you. So it's just a question of how the alkene coordinated to our platinum surface. Okay? So remember with that stereochemistry chapter, I made you draw on flip structures to try and understand their three-dimensional characteristics. This is part of it. Okay? Understanding how a molecule comes in and interacts with each of these generates different appearances of product. Okay? What would the relationship be between these two products that I've got drawn up here? Antimeres, diastereomers. Okay, let me redraw them, make them a little bit cleaner. Okay, if I draw out the attack where our hydrogen comes in, man, that was kind of rounded. From the back side, we've got our methyl group now coming at you. What's the relationship between my red structure and blue structure? Drawn another way, can we imply hydrogens? Is that an allowed move? Yeah, so let's simplify the red structure into this. Can we do that with the blue structure too? What's the relationship between these two? Identical. Pick the blue one up. It's a cyclopentane ring, the methyl aimed out. Pick it up, flip it over. We still have the cyclopentane ring, except now the methyl group is aimed away. There it is. These two products happen to be identical in this case. They look dramatically different, didn't they? Okay? So that's part of, again, being comfortable with Chapter 6, is manipulating these structures and seeing those differences. Okay? Next big reaction is actually an oxidation reaction. You'll notice that you don't see a whole lot of steps in this one. Any idea why there's not a whole lot of steps in this one? What? Kind of an easy answer. I don't really know the mechanism perfectly, and if I don't really know it perfectly, you don't need to know it really perfectly, okay? But the parts that you do need to know, and unfortunately you'll have to memorize it with this, is how the alkene reacts with osmium tetroxide and ultimately this next species, okay? So typically these would get written as a two-step process. You would see a 1, that's a 1, followed by step 2. You might see them stacked on top of each other over one arrow. Okay? So if I react an alkene with osmium tetroxide and sodium bisulfite, okay, what happens? I convert the alkene into a diol. What does diol mean? What does all mean? Alcohol. What does di mean? 2 alcohols. What do I have here? 2 alcohols. Okay? So when we look at this reaction, are there any notes that we could observe on this? Okay, so some simplifications that we could add here. The reagent takes an alkene, turns it to a diol. So we could have that memorized. What else could we write down about this reaction? What type of addition? Absolutely right. It's an addition reaction, and it's a syn addition. How do you know it's syn? Look at the product drawn. The alcohols are on the same side. They're both wedged. What if they were both dashed? Just checking. They would still be a syn addition. Okay? You won't see this one a whole lot, mainly because I'm not showing a mechanism for it, so I typically don't like to ask questions where we don't see mechanisms. Okay? Might be something that you'll see on quizzes. Okay? If I absolutely needed it for some functionality. Okay? Questions about these two reactions? I guess technically 3. Okay, because I'm pretty sure. Hopefully I don't regret this later, but I'm pretty sure I'm going to go ahead and stop it there because the next chemistry is a bit complex and I'd rather let this sink in.